Hey everyone, it's Luke again, and today I'd like to review a little bit about what we've done so far with AI and talk about where we can take it from here and what tools we have at our disposal. As you may remember from our last video, we worked out a way to get an AI to detect another unit within a certain range. This type of function, as mentioned previously, can have a huge number of uses in most games that involve AI that interact with one another or with the player's avatar. Beyond the obvious detection of an enemy, this sort of locational awareness will also be an important way to chain into various other aspects of artificial intelligence. As we noted earlier, it's actually easier to let a character know about everything. By default, Omniscience is the easiest way to handle AI because it's not difficult to achieve. At any given point in time, you can always get a full list of all other actors in a level. There's a node in Unreal 4 that accomplishes this, which we've used before, called Get All Actors of Class. The largest problem with using that unchecked, however, is that in the case of a game where you have hostile units, they'll always have an unfair advantage over the player because they'll always know where the player or the player's units are. As strange as it may sound, by limiting our AI's knowledge, or by constraining it, we're actually making our AI appear more realistic, and by proxy making the game feel more fair. This is going to be a running theme as we continue talking about game AIs, as it's one of the most important things to get right, and one of the most frequently done badly. Badly programmed AI is one of the most prevalent complaints that video game players have. Infamously, games like Far Cry had enemies shooting through walls, and its sequel, Far Cry 2, on highest difficulty, had every enemy in an enormous radius immediately aware of your location if you took a shot, and firing back with pinpoint accuracy, regardless of the player's attempts at subterfuge, or taking cover. While this can augment the difficulty level of a game, it's also a cheap difficulty spike. Enemies aren't smarter, they're just literally cheating. The all-seeing AI has its own page on TV tropes, which is certainly worth a look. But how do you implement a good AI? It's actually really tough. Obviously it is, or a lot of people would get it right. The function we created last week is a good starting point for starting to create rules for AI. But it alone wouldn't be enough in general. We need to further constrain our AI characters if we want them to behave correctly. Now, this won't always be necessary, I should note. You may not need to take it beyond this if the game isn't concerned with characters' individual knowledge. A good number of RTS games, especially older ones, tend to eschew more detailed detection except via what's commonly referred to as fog of war, which is basically one step removed from what we've already done. What fog of war is, put in simple terms, is a forced lack of knowledge of things outside the visual range of a character. If nobody in the army can see an enemy, it doesn't know that it's there. The characters can, however, gain knowledge of things based off of their previous positions. Let's take a classic, Warcraft 3, as an example. At the beginning of the game, all players are on a map, and only can see what's around them. There'll be varying levels of intelligence applied to any given AI, but in general, the AI will be told early on to begin scouting the map by making lesser units wander to waypoints around the map until they encounter an enemy structure, typically. They might engage the structure in combat, or they might turn back. Once they've seen the structure, though, they become aware of its location. Now, I don't have the chops to reverse engineer Warcraft's source code to see exactly what they do, but I'd surmise that when they see a building, they mark its location, or vector, in an array of known targets. Then they'll produce units and attempt to attack. Until they know about an enemy base, however, they won't begin attacking. It's really simple, but it can be the difference between a fair and an unfair game. Now let's start thinking about some more complicated games. In stealth action games like Deus Ex, the player, if not taking the brute force route to game completion, must use the environment to hide from their enemies and either avoid or kill them stealthily in order to progress forward. In modern games in this genre, most AIs have essentially two active senses, sight and hearing. Of course, these senses can't truly be simulated. This has to be achieved by considering how a character would potentially perceive another character. Sight is actually fairly easy since most people already have a fairly good idea of how they see things. You look in the direction that you want to look at, and you see a number of objects. Each object within your vision registers individually as something, and your mind processes that data accordingly. If you're looking for something specific, assuming you aren't like me and frequently miss things in plain sight, you'll pick that out of the objects that you can see, and you'll know that it's there. This works in theory a little bit like our getBestTarget function that we created before, though in its current iteration it doesn't assume two important things: the constraints of the character's vision and whether the object it's looking for is obstructed or not. So today we're going to be extending our getBestTarget function into an even more powerful tool of detection by adding a function that will allow us to check our cone of vision, or field of view. Firstly, we're going to want to consider vision. The most common method of determining sight is to use what's commonly referred to as a vision cone. The average human has a horizontal field of view of about 120 degrees. That's 60 degrees from the center of vision left and right, wherein the human is able to actively recognize objects. This is called binocular vision. You'll actually typically have significantly more sight capability in your peripheral vision, 180 to as much as 190 degrees or so, depending on your eye placement. But for our purposes, the limits of human binocular vision will be fine. Many games opt to go even more narrow, to even so far as the human symbol recognition limit, which is 60 degrees total, or 30 degrees in either direction. You can always tweak these numbers later on if a character seems too aware or too unaware of its surroundings. The way that we calculate this angle sounds tough at first, but it can be accomplished by asking the engine to do some very basic trigonometry. Don't worry, you don't need to know how to do it yourself, you just need to know what the engine needs to solve for. We can figure out the angle of a character relative to another character by getting the character who should be the source of the cone's forward vector, as well as a line between the two actors' respective world space vectors, normalized, then calculate the dot product of the two vectors, then solving for the inverse cosine of our dot product to get the view angle. It's complicated, I know, bear with me. The angle can then be compared against our preferred field of view, which will then tell us whether the character is within our character's cone of vision. What does that look like in the Unreal Editor? Well, let's build a quick function so we only have to do it once, and then we'll call it if it ever becomes necessary again. In our parent blueprint, we'll create a new function called ConeCheck, which will need an input, an actor reference called searchTarget, which will correspond to the actor that we're checking against our field of vision. We'll also need to define a field of vision for the character as well. It'll probably remain a default value all told as we go forward, but say we want something like a deer or another animal which has a much wider range of sight than a human. We can create a float, which we'll call FOV for field of view, as a variable in the parent blueprint, which we can then set at our leisure this way. It'll make things easier later on. Now let's compile quickly, and that way we can set the default value to 60 for our character FOV, in case we never want to look at it again. Now, inside the function's event graph, we'll drag a wire from our search target and get the actor's location. And similarly, we'll get a self-reference, which we will then use to get the world location of the actor calling the function. As with our distance checking math from last time, we'll subtract the two vectors to get a line between the two, but this time, instead of getting length, we'll use a normalized node to reduce the value to a unit normal, which is basically a simple directional vector. We'll need to get the forward vector of the instigating actor, which we can then use to grab that dot product that we just talked about. From there, we'll need to get the inverse cosine to get the view angle, which is called ACOS in Unreal. We'll make sure we're getting an angle instead of a radian. We'll then get a reference to our character's field of view variable and check that the ACOS is less than or equal to our defined FOV. Now let's get a return node from our output and add a Boolean output to it, which we'll call within FOV. This will be true if the ACOS of our little operation here is less or equal to what we defined previously, and then we can use that to define a branch. And there we have it. It's a nice little FOV function that will check to see if something's within the character's field of view, assuming that we set the FOV that we want. Before we wired it into our best target function, I'm going to add one little extra convenience to our function by defining another enum. As before, we create this from the content browser's blueprint generic group. I'll name this eCheckMethod. My idea here is to allow the scripter to choose whether to use the field of view or just to get all actors in a sphere like we had before. It'll make our function more versatile, which is the name of the game. In this enum, we're going to define two values: cone, which will be our cone check that we just made, and sphere, which will skip the cone check and just use the function the way that it currently works. Back in getBestTargetTown, implementing this enum necessitates us defining one more input, being the enum that we just defined, eCheckMethod. We'll pull the wire up and all the way over our sphere trace, along the way until we get past the branch after checking whether it hit another actor class. From here, let's replace our direct wire from the branch to the Add Unique node, and instead we'll insert a switch node that will allow us to define behavior based on the scripter's needs. Let's make some room over here first, and then we can rewire the sphere directly to Add Unique as it was before. The only big change from here will be, from the cone output, we get our cone check function that we just defined. And from within the FOV pin, we'll create a branch, which means the game will only add hit actors that are both of the correct class and are within our character's FOV at the time of the function call. We'll get the actor reference from back here. And that's all we needed to do there. One final step before we test though. Let's fix our actor's rotation. Has this been driving anyone else crazy yet? I mean, I meant to do it a while back, but here we are. And now it's fixed. Hooray. Okay, let's go into our AI NPC blueprint as always and take a look at our getBestTarget node. Note that we now have a checkMethod dropdown. Let's change that to cone and give her a test. And there it is. I know it doesn't look that different from before in testing, but note that as our character turns their back to the other AIs, that the list no longer updates. There we have our cone of vision. Next week, I'd like to talk about line of sight, and since LOS is fairly simple, we may just get on to some behavior derived from all this detective work that we've been doing. But until next time, thank you very much for watching, and take care.